Hello, everyone. I'm Zuzanna Kabacińska. I'm very grateful for this opportunity to talk to you today and for this invitation from the Polish Center of Mediterranean Archaeology. I work at the Geochronology Research Unit at the Institute of Geology at the Mickiewicz University in Poznań. But as it was mentioned before, I'm actually a physicist. I did my PhD in physics also in Poznań at the Mickiewicz University. And I also studied archaeology. So the bachelor degree I obtained also at the Mickiewicz University. And I work at this interdisciplinary field between physics, geology, and archaeology, mainly using dating methods. Before I came back to Poland, I spent 2 years in Romania, working in 2 ERC grants as postdoc, and they were led by Professor Alida Timar-Gabor, and they were connected with EPR and luminescence dating, mostly applied in geology. Since last year, I am leading a project at the Institute of Geology. This is Polish Returns NAWA project. That is addressed to Polish researchers who spent some time abroad and now they want to come back to Poland and start their own project, their own group. And this project is devoted to establishing EPR dating of lime mortars. So today I would like to tell you about electron paramagnetic resonance, or the method I'm using, its principles and its applications, mainly in dating. And the second part of the presentation will focus on those first results from the NAWA project of EPR dating of lime mortars. And before I dive into EPR, so electron paramagnetic resonance and its physical principles, first I would like to tell you more about this group of methods. Yeah. I don't know where to aim.
Check that.
Oh, okay. I guess I will aim there. Sorry. Okay, so we have several groups of methods that we can use for absolute dating. Probably the best known are isotopic methods like radiocarbon dating, sidereal methods, so those that are based on the cycle of the sun, like dendrochronology. Then we also have methods that are based on chemical or biological processes, geomorphic processes, and the methods that have to be correlated with some independent data to estimate the age. And then we have the group of radiogenic methods, so those that are based on radiogenic distortions of crystal lattice. And here we have fission track methods, the method that I'm not going to talk about today, but what I will like to talk about is the group of trapped charge dating methods, so electron paramagnetic resonance, thermoluminescence, and optically stimulated luminescence. They are all based on two fundamental facts. So first, the presence of defects in the crystal lattice of minerals, some imperfections that can work as traps for electrons. Secondly, the presence of radioactive isotopes in the soil, in the environment, which constantly produce radiation that affects the minerals that are placed there. So during this radiation, electrons in the material, in the crystalline lattice, they are excited and they leave their natural positions and they can be trapped in those defects, in those impurities of the crystal. Then they can be stored in those defects for a long time because they don't have sufficient energy to leave. And when we give some additional energy to the sample in the form of light or heat, they can be freed from those traps, and we call that process breaching. And during this breaching, this energy that was stored in the material is now emitted in the form of luminescence. The intensity of this luminescence is proportional to the number of trapped electrons. We can also present it in the form of this graph. So from the moment of mineral formation, we have the growth of the signal. So the number of those trapped electrons increases. It increases exponentially because there is only a certain number of traps that can be filled in the material. And when they are all filled, then even though the material is still exposed to radiation, it just cannot trap more electrons. Then when the sample is exposed to light or heat, for example, during transport or during heating, the signal is lost, is bleached. And from this moment, then when it's deposited again in the ground, then the signal rises again until we collect the sample and we measure it in the laboratory. And in luminescence, we again heat or illuminate the sample in the laboratory and measure this luminescence that it produces. So the age that we can calculate using those methods is actually the age from the last light or heat exposure. If the material was not exposed to light or heat, then it's the moment of mineral formation that we can date. And this number of trapped charges is proportional to the dose that is absorbed in the material. And this process is used for dating using those three methods. What is different about them is the technique of measurement. So in thermoluminescence, TL, as the name suggests, we heat the sample. Optically stimulated luminescence, OSL, is illuminating the sample. And electron paramagnetic resonance is a bit different because we actually measure the sample when it's exposed to microwaves in the magnetic field. So we do not bleach the signal during measurement, but we just see what response those trapped electrons give. And together, those methods are referred to as trapped charge dating methods. To actually calculate the age of the sample, we need to know two values. We need to know the geological dose or archaeological dose, so the dose that was absorbed by the sample. And this is the value that we get from TL, from OSL, or from EPR. But we also need to know dose rate. So it's the dose of radiation per year at the place that the sample was collected from. And we measure it independently, either in the field using a dosimeter or in the laboratory by analyzing the sediment that surrounds the sample and the sample itself. Because this dose rate is actually the sum of external dose, what is around the sample, and internal dose, so the isotopes of the sample itself. Then how we can calculate this geological dose? So we can use the additive dose method. And in this method, we take our natural sample, we measure the signal that it gives, and then we irradiate this sample in the laboratory with known doses of radiation. And therefore, we create this curve that shows us how this material reacts to radiation. We call it a dose response curve. And then when we extrapolate this curve, use the cursor here, when we extrapolate this curve to the point of the intersect with the x-axis, what we get is this value. So this is the dose that the material had to absorb to produce the signal that we naturally observe. We call it an equivalent dose, and we assume that it is equal to the absorbed dose of the material. Alternatively, we can use our regenerative dose method, and in that approach, we bleach the sample after measurement, or actually during every measurement, and then irradiate it again. So we bleach and irradiate with every dose. So this curve is basically just shifted, but the idea is similar. When it comes to dated materials using those methods, basically they are crystalline materials. So it can be quartz, feldspar, carbonates in the form of shells, corals, speleothems, bones, and tooth enamel. Not each of this material can be dated by each of those three methods, but in general, this is the group. As I mentioned, the dated event is the last exposure to light and heat. And the time range of this method for TL and for OSL ranges from a few tens to about 1 million years. And for EPR, from usually thousands and possibly a few hundred years to over 2 million years. For sample collection, the most important thing is that it has to be protected from light, because light will bleach our signals. So if you want to collect some loose samples, like from the sediment, a good method is to use some metal tubes that we can hammer into the profile. So then whatever is inside the tube is actually protected from light. And what is on both ends and was exposed during sampling then can be this tube can be opened in the darkroom, and those two bits at the beginning and at the end can be removed, and that can be used for dose rate estimation, because for that it is not important if it was exposed to the sunlight or not. Alternatively, we can collect the sample under some sort of cover, or if it's a big bulk sample, then we can collect it like that, and then in the darkroom remove the outer layers. We also need to remember to collect, if we collect some bulk samples, to collect the sediment around it for the dose rate. If we have such an option, we can also collect those samples in the dark when we are in the building or in the cave with some darkroom lights, so red lamps. Here, for example, we collected some samples of mortar from the Benedictine Abbey in Tyniec. So we were doing it indoors, so we could actually use lamps like that. An important thing when it comes to choosing the place to collect our sample from is that the sediment around the sample should be homogeneous, if possible, because if it's not, then different components can give different radiation, and estimating the dose rates then can be quite complex and difficult. Okay, now moving to EPR spectroscopy. It functions under two names, Electron Paramagnetic Resonance or Electron Spin Resonance, so EPR or ESR, and they are both interchangeable. In English, usually ESR is used, and in Polish, usually EPR. In Polish, it's Elektronowy Rezonans Paramagnetyczny. This phenomenon, EPR, is observed only in substances that are paramagnetic, so those that have unpaired electrons. And we have different types of those paramagnetic centers, so those that we can observe using this method. They can be radicals, they can be ions of transition metals and rare earths, molecules with unpaired electrons, conduction electrons, and defects of crystal lattice, which can store some unpaired electrons. And those defects can be caused by a mechanical treatment or by high energy radiation, and they can be called radiation defects then. And those will be the ones that are interesting for us in terms of dating. But EPR is not only used for dating in archaeology and geology. It's used in many fields of science, in physics, chemistry, biology, agriculture, and food science. So it has really various uses, various applications. When it comes to understanding the principles in EPR, a very important term is magnetic moment. So simply speaking, it's the measure of objects' tendency to align with magnetic field. So because electric and magnetic fields, they are connected with each other, and change of one causes the other. When we have a cable with a current flowing, it produces magnetic field. When we have a loop with a current flowing, it also produces a magnetic field. And if we imagine a rotating ball that is charged, that flow of charge will also produce a magnetic field. So this rotating ball will have a magnetic moment, and we will also have the angular momentum because of its rotation. And this is a pretty good approximation of an electron, because electrons have spins that we can imagine as being connected with the rotation. It's a bit more complex than that, but it's a good way to imagine it. I found this great image in the internet, how to explain electron spin. So imagine it's a ball that's rotating, except it's not a ball and it's not rotating. But I guess we can use that approximation. So electrons form pairs that spin in opposite directions, and we call them paired electrons. And EPR allowed us to detect only those that are unpaired, the unpaired electrons, so the single ones. And if we put our sample in the magnetic field, in this external magnetic fields, those magnetic moments, they can have two energy states. So they can be oriented with or against magnetic fields, and therefore can have lower or higher energy. And we can cause a transition from this lower to higher energy state, and we can cause this magnetic moment to flip if we provide some energy to the sample in the form of electromagnetic wave. So we need to exactly fill this gap between those levels. We can fulfill this so-called resonance condition. So on the one hand, in this equation, what we have is Planck constant, and we have the frequency of this electromagnetic radiation that we bombard the sample with. And on the other side, we have a value called a G factor, which is characteristic to every paramagnetic center. We have another constant called Bohr's magneton, and an induction of external magnetic field. And if we forget for a moment about all the constant, and focus only on the values that we can change. Those are frequency of electromagnetic radiation and the induction of the external magnetic field. So those two need to find the right combination, and only then we can actually see this absorption, and we call that process magnetic resonance, hence the name of the method. And because different paramagnetic centers require different amount of energy because this transition from the lower to higher state, this resonance will also occur at the different combination. So for different values of the magnetic field induction, if we keep the frequency constant, which we do in EPR method. And therefore, the signals will also appear at the different positions of the spectrum. And normally, we would expect this absorption signal to appear, but what we actually register in EPR is the first derivative of the signal, so it has a bit of a different shape, but because of this shape, we can also distinguish the signals better if they are close to each other. And EPR is not as well known to the general public as similar methods, nuclear magnetic resonance. So this is basically the resonance that we know from hospitals. And there are three main differences between those two methods. So first, the main concern of EPR are electrons. And for NMR, they are nuclei in the atoms. And because of that, also this electromagnetic frequency that we use will also be at a different range. So for EPR, we use microwaves. For NMR, we use radio waves. And here lies the answer to the question why EPR is not as commonly used in hospitals in medicine. Because we all know what happens to the material when we expose it to microwaves, because we see that in our kitchen using microwaves, so that will cause the heating of the object. We wouldn't like to cause that. However, now there are some technical solutions that allow for imaging of small animals, for example, using some safe ranges of electromagnetic radiation. And thirdly, there is also a bit of difference in the method of measurement. So for EPR, we keep the frequency constant and we vary the magnetic field. And for NMR, the frequency vary and magnetic field is kept constant. Here we can see an example of a spectrometer that is used in this method. It's made component actually. So in the center we can see this electromagnet, which is very heavy, and on top of that, this part is the microwave bridge. So this is what generates the microwaves, and they are then transported here to the resonator, where we actually place our sample in quartz tubes. This particular spectrometer is located in Romania, in Cluj-Napoca, at the Babeș-Bolyai University, where I work, and when I also did the measurements that I'll present later on. And now there are also some smaller models available, benchtop models, that can also be used for some purposes, for the EPR spectroscopy. When we see the EPR spectrum, we can use certain parameters to identify the signal. So, of course, we can look at the position of the signal. We can look at the distance between lines. We can measure the amplitude of the signal and its width. Here, the signal is very simple, but in fact, often those spectra are quite complicated with a lot of overlapping lines. A very important parameter is this G factor, which I mentioned before. So this value allows us for identification of paramagnetic center. And it is very sensitive to the symmetry of the field that surrounds our paramagnetic center. So if the symmetry is isotropic, so in every direction it feels the same things, it gives a singular signal. When the symmetry is axial, we then see two components of the signal, and for orthorhombic signal, we actually see three. So then if we add to that some other effects, like the interaction with the nuclei in the atom, and we imagine that we usually don't have just one, but several paramagnetic centers in the sample, then we can often see a lot of lines on the spectrum, and we need to interpret it. So this interpretation can be challenging, but it can also provide a lot of information about the structure of the material and the interaction between the centers. When it comes to EPR dating and the materials that are used, I already mentioned what groups of materials are used for capture dating methods. And for EPR specifically, it actually started mainly with carbonates in the 80s, but then gradually the amount of publications that deal with dating of carbonates was lower and lower, and now quartz is the most popular method, most popular material dated with EPR. The second most popular is tooth enamel and bones. As I mentioned, the range of EPR dating is from a few hundreds or usually few thousands years to over 2 million years. So it is larger than for luminescence and shifted a bit into the past. When we want to date quartz using EPR, we focus on two main signals, one collected with aluminium complexes and the other with titanium complexes, which are some impurities that are always present in a quartz grain. We can already see that those signals are a bit more complicated than those that I showed before. And those particular ones are only visible in very cold temperature, so in liquid nitrogen. So we measure the amplitudes of those signals and irradiate the sample in the laboratory with different doses, each time measuring the amplitude. And from that, we get our dose response curve. And from that, we can estimate the equivalent dose. For dating bones and teeth, we focus on hydroxyapatite, which is the main component of tooth enamel, dentin, and bones, particularly on carbonate ions that are present in the crystalline lattice. This signal here is simpler. We can also measure its amplitude and create a curve. Specifically dating of tooth enamel, it presents some, I think, very practical solutions, especially for archaeologists, for some samples that are quite rare, and we wouldn't want to destroy them because in general, those samples need to be crushed for smaller grains and measured like that. But for tooth, it is actually possible to remove a fragment of the tooth, measure it under different directions in the magnetic field, and then put it back. So that is, I think, a great option for archaeologists and for some very rare tools. Okay, now moving on to the second part of the presentation. I would like to talk about the first results of the project. This is Polish Returns NAWA project, focusing on radiation defects in anthropogenic carbonates and the possibility of dating them using EPR. So the first step of this project, which is close to being completed now, focuses on investigation of EPR signals in lime mortars that were previously dated with radiocarbon and were well characterized. And here I have to say that because they were collected for radiocarbon dating and not EPR or luminescence, they were exposed to light. They were not kept in the proper conditions, so therefore they cannot be used for dating. And we also don't have the information about the dose rate because it was not needed at the time, so it was not collected properly. However, they are a very good basis to know more about this material, what kind of centers we can expect, because they are so well researched already. And as you can see, even though those particular samples, I will show that later on, were not properly collected, they can still exhibit some signals. And in general, in EPR, in carbonates, it may not be as necessary as for luminescence and for quartz. Then the second step that we are starting around now, it will focus on manufacturing lime mortars under laboratory conditions and analyzing the EPR spectra before and after irradiation. So that can allow us to assess the lower limit of detection of the dose. So we'll irradiate those mortars with different doses, and we will see at what point we start to actually see the signal. And from that, we will be able to say how young can some potential samples be. Then the third step will be actually EPR dating of properly collected samples of lime mortars that were previously dated with OSL. So they have a known dose rate and were also well characterized, and that will be a great opportunity to compare the results with an independent method. It's important to note that although this time range for EPR exceeds 2 million years, there are virtually no examples of dating carbonates younger than 10,000 years. They are basically just 2 or 3 examples that I could find. And of course, mortars will be younger than that. So here lies the main challenge of this method, that for very young samples, those signals, they didn't have enough time to grow. And for some of them, they might not be visible yet. So in the further steps, we'll focus on that to see when actually we can start seeing some signals. Okay, first maybe a few words about lime mortars, how they are being produced. So they produce by thermal decomposition of limestone, and then subsequently by mixing it with water and leaving it to harden. And through the absorption of carbon dioxide from the atmosphere, this mortar hardens and it forms new calcium carbonate crystals. So currently, we can use today 2 methods to date mortars, radiocarbon and OSL. And radiocarbon dates the time of hardening of the binder, which will be related to time of the building constructions. And also dates the last bleaching, so resetting the signals by exposure to sunlight of the quartz grains. This quartz is added as sand, as an aggregate during the production process. But those methods have certain limitations, and for OSL, it's the incomplete bleaching of quartz grains. So although we assume that during the production it was exposed to light and it was bleached, it may not always be the case. And for radiocarbon, this limitation is the presence of unburnt calcium carbonate, or some carbonate aggregate that was added to the mortar and was not burnt, and therefore it is older than the mortar itself, than the binder. So for this project, I propose to use EPR for dating. And it will focus on the carbonate binder and will date the time of hardening of the binder. So forming those calcium carbonate crystals, and additionally also resetting signals by heating. So those fragments that were not properly decomposed and hardened still were exposed to very high temperature, high enough to bleach the signal. And this double mechanism of resetting the signal have the potential to overcome those difficulties that we deal with OSL and radiocarbon. And additionally, we also have the potential of eliminating some unwanted signals using simulations during the step of spectral analysis. And the EPR measurements of lime mortars were already conducted by me some time ago during my master thesis. So already around 15 years ago, we, together with Professor Zuzanna Michalska, that is now also a part of the project, we have this idea that EPR has this potential to be used for dating. However, it required more research, and now finally, after all these years, we do have this opportunity to research it from the very beginning and see if EPR can actually achieve this goal. To this date, I measured around 40 samples of mortars using EPR. But here for the presentation, I would like to show you the spectra of just a few of them. So those are samples from an ancient settlement in Hippos in Italy. And those are also samples that took part in MODIS project, so mortar dating and comparison study, that compared the results and the procedures from different labs for radiocarbon and for OSL dating. And those are a sample from a burial site in Majorca, a church in Finland, and a Christian basilica in Spain. And finally, a group of samples from the royal castle in Poznań at Góra Przemysła. They were dated by C14, and the data were published, including characterization done on the samples. And this characterization and preparation included crushing, sieving, and sometimes separation of binder in suspension. And characterization was done by petrography, SEM plus EDS, and XRD. As mentioned before, those samples were collected and prepared without protection from light. We also don't have dose rate data, so they are actually not for EPR dating, just for testing the materials and the procedures. And they were also for EPR measurements irradiated at the Technical University of Łódź. Measurements were done on the EPR spectrometer in Cluj-Napoca in Romania at the Institute of Bio-Nanosciences. And I conducted EPR simulations using an easy spin software and some parameters that I previously published in some works connected with carbonates. Okay, so when we measure lime mortars, and in fact all carbonates using EPR, we can pretty much always expect a very characteristic signal that is connected with manganese ion. It has those characteristic 6 main lines and 10 additional lines. And between the third and the fourth line, so in the very center, we have this region in which we can expect signals that are correlated with trapped charges. So datable samples should already have some signals in the natural sample present in this fragment of the spectrum. It's important to note that this manganese signal can be used for provenance studies for limestone and marble, and there is quite a lot of literature about that, but it uses generally the shape of the manganese spectrum, which can differ depending on the material, therefore the site that it was collected from. Okay. Here I gathered the spectra of the samples that I described. So this is this region including the third and the fourth manganese peak. And we can see that pretty much in all of them, in the center of the spectra, we can see some additional lines. Now the question is whether or not they are connected with some trapped charges and if we can use them for dating. For some samples, we didn't have enough materials to actually conduct the irradiation, because then we require more of the material to divide it into portions and send it to irradiation. But there was enough material to do those kind of research on some of them. And firstly, we have the sample from hippos. And we can see that after irradiation, up to 800 grays, what is visible is that the signal's amplitude change. They grow with irradiation. I conducted those simulations, and simulations are basically, we can say, dividing a spectrum into components, but it actually is simulating those individual components based on the data from literature and the observation of the spectrum, and then adding them together to get a spectrum that then we can fit to the experimental one. So we can see those different components here. We can see that there are carbonate signals, there are nitrates, sulfates, and organic radicals. And here the spectra of carbonate ions and perhaps also nitrates are very promising, because carbonate signals are those that are used for dating of carbonates using ESR. For the sample from Majorca, this growth with the radiation dose is even more prominent. Again, I conducted the simulation, and there is even more components in case of this sample. So particularly, we need to notice the carbonate signals, so isotropic and orthorhombic CO2 minus signals. And because we were able to obtain more doses for this particular sample, I could actually try to do this dose response curve. So for every dose, I simulated the signals and measure the intensity of the signal. And I could obtain this equivalent dose. But once again, let me stress that those samples were not collected as they should be. So those data may not reflect the natural intensity of the signal. So it's mostly for to visualize how it could be done. But to actually obtain the age, we need not only the equivalent dose, but also the dose rate, which we also do not have. And when we look at the literature, we see that for some OSL dated mortars, those values of dose rate they range from 1 to 10 milligrays per year. Although they were actually calculated for quartz grains, not for carbonate grains. And because in the preparation of quartz, we actually etch the sample and we get rid of the outer layer of the grains that was exposed to alpha radiation, then we didn't need to take that into account. For carbonates, we don't do that. So the alpha component will also have to be taken into account. So assuming because of that the dose rate closer to the upper part of this range, let's say 8 milligrams per year, that would give us the time of from 2,800 to 3,900 years. That would actually fit well within the range that was estimated from radiocarbon dates. But I'm stressing once more that this is not actually dating. This is just based on assumption to visualize what would this potential of this method be. And lastly, this group of samples from Góra Przemysła, here is a bit different because after irradiation, although we do see some changes, they are actually not prominent because for this sample, the main signal is actually connected not with some trapped charges, but with amorphous carbon, most likely, presumably produced by pyrolysis. So we don't actually see some signals, we don't see some carbonate signals that can be used for dating. However, this may be also addressed through some proper preparation, because recently I measured a sample from the same site, generally quite similar, but prepared through this sequential dissolution. So we assume that the binder is more loosely connected. So when we make a suspension and we remove only the top part of the suspension, we can actually hope to get this binder instead of some other older elements. So if prepared like that and measured, this sample actually didn't show this carbon signal anymore, but a range of other signals, most likely some sulfate centers. So here there is a potential that with proper preparation that can be resolved. So to sum up, first a few thoughts about the EPR itself and its use in dating. So EPR spectroscopy detects unpaired electrons through the response to microwaves in a gradually changing magnetic field. It can be used for dating crystalline materials in a range of a few hundreds and more often a few thousand years to over 2 million years. And it dates the last exposure to light or heat. EPR studies can give us a lot of different information about structural data. And in case of dated materials, what it actually gives us is the concentration of trapped charges. But to obtain the age in EPR, as well as OSL and TL methods, we need to know the dose rate for the sample. The samples need to be protected from light and heat during sampling and during the preparation. And when it comes to dating mortars, establishing EPR as a new method will allow us to overcome some difficulties that the other currently used methods face. And it will also extend the time range of EPR dating closer to the present day, which is relevant not only for mortars, but also for carbonates and EPR dating methodology in general. So I would like to thank you very much for the organizers for this invitation, and also the participants of the MODIS projects, particularly Professor Ilka Hajdas and Professor Alf Lindros, and Professor Alida Timar-Gabor from ESR Dating Laboratory in Cluj-Napoca. And to acknowledge that this Polish project, Polish Returns project, is funded by the National Agency for Academic Exchange and partially by the National Science Center. So thank you very much for your attention, and if you have some questions, I'll be happy to answer them. Thank you.